All right, so today's lecture is about priority queues. It's a very cool data structure, and it's really good for managing data that you don't always have at the same time. So I would call this a dynamic content. So what do I assume that you have? Essentially, that I assume that you have some kind of a prior knowledge about basic Java coding, and you can read some basic Java code. And also, I'm going to assume that if you're given a piece of code, you can look at the piece of code and think about how many operations. You can count the operations and come up with a formula and come up with the order of growth. Order of growth means that you have some formula. Let's say you come up with 2n squared plus n, where n is the number of the data size, and you drop low order terms and the constants. We call that the order of growth. And some background in discrete math, although it's not really necessary to understand this structure, and maybe some understanding of mathematical series and summations. Familiarity with the basic concepts of loop invariant. Um, so also know some of the basic data structures that we're going to be talking about here. So that's sort of the prior knowledge, and the uh, sort of the lecture outline will be I will talk about the API for priority queues and sort of implementation of a priority queue using a binary heap. And we'll talk about some of the operations and how to build a heap from a given set of data with some analysis, and then implementation. We'll write some simple code, and then talk a little bit briefly about the loop invariants and applications that can be interesting. So let's put some background into our discussion today. And I'm going to start with collection. So it's a collection is like a it's an elementary data structures that supports some operations like insert, delete, modify. So we can have collections of uh, generic elements that are held in a certain way. So we can either put them in a stack, we can push and pop in, say, the constant time, or we can put them in a queue, first in, first out, or randomized queue, unq and dq a random element, or put a hash table and find it. So in all these cases, you have to have some comparator, some way to compare elements, perhaps, or some orders, some comparison criteria to perform this. But all of these elementary data structures or the collections are very efficient ones. We can pretty much implement them in constant time for inserts and deletes. But some clients may have different requirements. So let's look at a few client scenarios. So the first scenario is essentially client one come and say, I have a data set that's dynamic. That means it comes often and data may arrive over a period of time. I have to process the data in the order they arrive. I can only maintain a fixed data set. And I want to minimize the average processing time for all. So in other words, each data set can have a processing time. And I want to look at the average processing time for all the data and minimize it. So the if that if so, what data structure should I use? Suppose I have a bunch of data comes in, and I will process them in the order they came. And so while I process the first ones, the others have to wait until I take them out of the queue. So I have a queue of a fixed size. So let's suppose I use a queue to do it. So in this case, I will have to compute the total processing time because some have to wait. So it adds them up. And so I will come up with something. So here's an example. So here, let's suppose that we have this data set and we try to find the average processing time for this data set. So this is what we get. So on average, it takes this much to do. And client two will say, okay, I have a data set. It's the same conditions, but my job is different. I want to find the smallest k elements of n, and n can be huge. So I can only have a fixed size data set. So I can't maintain all the n. I just want to maintain the smallest k elements, but they come in different times. So what data structure should I use? So suppose we use a random array. And so for instance, we can have, let's say the first k elements go into this, the next k plus 1th element come, then I have to decide whether to kick out one of the other k elements and push this guy in or just not accept it. So in any case, it could cost, in the worst case, it could cost up to k operations to do it. So we have, so for all the other elements other than the first k, there are n minus k of them. We have to do k operations to figure out whether they go into the list or not. At the end of n elements, we have the smallest k elements. So to figure out whether all those n minus k elements go into the list or not, we have to do n minus k times k work, which is n times k. That is quadratic. That can be very large. So it's probably not a good idea to use a random array to do this. So one observation we make is that maybe if you have a collection that can find min-max efficiently, can support these client requirements. So we will go back and look at our example of first in, first out queue and say, what if we ordered this in a different way? So let's suppose that we have a differing ordering of the data. And if we do that, then what we can do is that we can compute now the average time. Let's suppose that we will process them by taking the next smallest thing. And now the answer changes to be 16. So you get quite a significant gain by reordering things in a different way. So the observation that also this one here, if you want to find the smallest k, then we can put them into some collection, and this collection can find the min or max efficiently. So what we do is when the kth element, when all the elements, first k elements we add without even looking at it. And the next element, when we add, we remove the maximum of those k plus 1 elements. So we have the current smallest k elements left. So in that case, we still do the same thing. We just add something and then remove the max, add something, remove the max, and so on. So we do that n minus k times. So what we need is a special data structure to support these operations. So let's call it a max PQ. Okay, so we will say we'll support these find max, insert, delete max operations very efficiently. So we'll define a priority queue API, some kind of interface. So essentially, we're going to assume that it has a priority, so it must be some comparable keys that we're going to put into this priority queue. And they must be comparable. And a possible Java definition would be that a public class max PQ has a generic key type, which is a comparable key. And it has a constructor, creates an empty priority queue, or create a priority queue from an array of keys. Given a key, I can insert the key into the priority queue by a priority of the key, and I can delete the max and return that key, or I can check whether the priority queue is empty, or I can return the largest key by some comparison criteria, but not remove it. Okay, so now let's think about how we implement a priority queue. What can we do? What kind of a container can we use? So let's think about some of the known data structures. So can we use this as containers, and what would that cost? For example, if I use an unordered array to maintain the priority queue, my goal is to provide an API to support these three operations. Finding a max in an unordered array is what? N. And inserting something, it's easy. We just stick it into the back of the queue, back of the array. Deleting, again, you have to find it and delete it. Once finding is the expensive part here, deleting the max is not difficult in an unordered array if you know where the max is. And then, so if you figure out what the operation cost is, order of growth is going to be in terms of n, the data size, that's going to be the one. If you have an ordered array, it kind of changes. essentially that you can find the max because you would say max is the last one, or deleting the max would be easy, and inserting something you have to maintain the order invariant, so it's going to cost you n. Unordered linked list, you can say I will find the max by going through the entire thing. I can always insert it to the beginning because I don't really care about the order. And if you have an ordered list, you have to maintain the order invariant, so the insertion will cost you n. But I can find the max and delete the max. Perhaps we keep the max at the beginning of the array. If you have a stack, again, inserting is not difficult, but finding any kind of order is expensive. Perhaps I put a star there, so you have to use some extra space to do that. A queue would be this same kind of a thing where you have to probably take them out and figure that out. If you have a hash table, yeah, it's easy to insert if you have a uniform hash table. But again, finding any order in a hash table is difficult. So our goal is to find something of this. We want to find a data structure that can do these things. Find max in one and insert in log time and delete max in log time. One can ask the question, can we do better? Let's suppose, can we find max, insert, delete max of any data set in constant time? Can we? Well, why not? So let's assume we can. Then we can insert n things and build this data structure. It would cost us n. We can delete max n times because each one is constant time, so that would be constant time. So that means we can really sort an array in some kind of linear time, which we know is not possible because there's lower bound for, what is the lower bound for comparison-based sorting? It's going to be n log n. All right, so let's take a quiz break and think about this question. I'll let you think about this and we'll talk about okay, let's take a few minutes to do that. All right, so let's see what happens here. We want to know what's the output of the above code is. For example, let's assume that insert, okay, before that, let's talk about the output. So we created max PQ and I set to 0, and then while I is less than n, so we're getting some n things, we insert the key I into the bunch of keys. We put the key I into the set, into the priority queue. And if the size of the priority queue is greater than k, we delete the max. And then after we exhaust n things here, then we will go and print it. So the output of the code is going to be, I think what you have to recognize is that every time we insert something, we delete the max if the size is k. So we're maintaining a priority queue of size k, but so it's the k least element of the thing. So what you're printing is the lowest k keys in n keys. So what if we remove this? If you remove this, then you will build a priority queue of size n, and then you print the first top k elements of that. So we print the highest k elements of these n keys. What's the order of growth? Let's assume that insert, delete, max are order of growth log n. Our ideal data structure, log n, we can do insert and delete max. So if you think about that, then what we can say is, okay, there's a loop running n times. Inside the loop, I will insert, so that to insert each element, that would be log n, because it's a priority queue of size n. Well, I think this is interesting because what you have is a priority queue of size k, right? Because a queue would never go beyond size k. So insertion cost would be k. So to insert, it's k. And to delete max, we delete max n minus k times. So delete max would cost you k, log k operation. So this is log k, n minus k, log k. So for this part, we will have to do n log k. So because we have to insert n things into a priority queue of size k. And then we delete max n minus k things. That's the n minus k log k. And then we would print them k things in by deleting them, so that's k log k. So that's the answer. Okay, so the question now is, how do we implement a priority queue? We know the arrays and stacks and queues did not look good, so we'll have to think of something different. So I'm going to start defining a structure called a complete binary tree. We're all familiar with binary trees, so it's each node has at most two children. So complete tree is it's a binary tree and a complete tree. Complete tree means that all levels are full except the last level, which is filled from left to right. So here's a complete tree of one node, two nodes, three nodes, and so on. If you look at the height of these a complete tree, if you have one node, then the height is 0. If you have two nodes, height is 1. Height is 1 here. Height is 2. Height is 2. So we define the height as the number of nodes, number of edges from root to the lowest leaf. So height is 2. Height is still 2. So, but if you go to the 8 nodes, then you will add something here, and so height becomes 3. So in other words, when n is 8, some power of 2, the height increases. So when the height became 4 from 3, it increases the height. So it became from 1 to 2. So in other words, when you go from 2 to the power n to 2 to the power n plus 1, so you have twice as many links. So you can add, I mean, you go from 2 to the n, you get to the 2 to the n thing, it increases the height by 1. So we will use that to argue that the height of the tree is logarithmic. There are a few things that we will define. We will define a structure called a binary heap, which has two things. One is the shape invariance. So there are two invariants that needs to be satisfied for a binary heap. It has to be a complete binary tree, and it must have some order. So in the case of max heap, we'll say each node, the key is greater or equal to the children's keys. We will allow duplicate keys, unlike binary search tree, we will assign a duplicate. We will allow duplicate keys. So how do we represent a binary heap? Obviously, we don't want to do this. We want to do this as cheap as possible, and we don't want to deal with the left pointers and right pointers. So we think about a nice way to represent the kind of complete tree that we discuss. So in other words, we think of the tree where the indices, we don't use the 0th index, but we think of the trees, the root starting at index 1, and the left child of 1 would be 2, right child of 1 would be 3, and left child of 2 would be 4, and right child of 2 would be 5. So if we think like that, then we have some kind of if you take nodes in level order, so if you go T, S, R, P, N, and so on, what you see is that the nodes are compactly, these are the indices of the nodes 1, 2, 3, 4, 5, 6, 7, and they are compact within the array. And the nice thing about this is that we have a representation of the binary heap. Is this a binary heap? We can always test that. We know it's a complete tree, so shape invariant is satisfied, and also the order invariant. So if you look at parent is greater than or equal to its children. And we can also traverse, we can also think of this, write the code as thinking this as a tree, because if you want the children of AK, we just simply look at A2K and A2K plus 1. If you want the parent of, that should be AK, we look at the AK over 2. Let's take a quiz break. So let's say we define the height of the binary tree as the number of edges in the longest path from root to the lowest leaf. That's the height of a complete binary tree with n nodes. So it could be log n, but it could. So it's so log n. If you have like 3 nodes, or if you take like log 3 or log 7 or log 6, it seems like the height is a log something, but is it the ceiling or the floor? So we got to decide. So if you take something like log 7, something like 2 point something, right? Log 6 is 2 point something. If you go to log 8, that's 3. So, but when you go to 8 from 7, your height increases to 3. So log 8, it's a flow, that you want. All right, so let's think about some of the operations we want to do with binary heaps. So we said that in the beginning, we want to insert something, we want to delete something, we want to find something. So those are the basic operations, right? So we'll see how we can do that. So if you have a binary heap represented as, if you have a priority queue represented a binary heap, we know that if you have to return, find the max, it's always the root, which is the array, it's represented as an array of PQ of 1. And the cost to get that would be 1. I'm not removing anything, I'm just getting it, right? So that's easy. Inserting something, I will insert to the next available index, which is this one here, and which is like adding to the end of the array, and then I will try to move it up the tree. So the next thing I will compare z with h and say, okay, z is bigger than h, so I'll swap those, and then I'll compare z with p, and that's still bigger, so I will move the p here, move the z here, and then I'll compare with t, and then that's still bigger, so the t comes here and the z comes there. So essentially, as I go through to insert this element to the beginning, to here, even all the way up to the root, and we call it swimming up. It took 1, 2, 3 comparisons and 3 swaps to get there. So it's an efficient operation, so it's log n time. You can get some intuition for that. Okay, what about delete max? So the delete max would be some operation like this. So suppose you want to delete the max, so that means you want to get rid of this. So what we do is we swap this A1 and the A of size plus 1. So that means we're gonna swap these two things. And so we put the G in here. So that means the G, T and G are going to be swapped, and eventually T is going to be deleted by just reducing the heap size. So once we put the G here, then we have to compare G to these two, and we have to sync it down um, while maintaining the heap order property. So we're going to just compare them, G to these two, and figure out which G's. So obviously, we compare it to both of them because we have to make sure that G's. If you find one of them, then you can just swap with the R and send it down this way, or you can swap with P in this case, I guess, right? So the P would go here because that's bigger. No, it cannot be. Oh, you have to find the max of these two. So you have to find the max of these two, and then place it here, and then move the G down that path. So again, you will only go through one path of length n, log n, and so it's an efficient operations to delete the max. All right, so we have another quiz break. So here's a quiz. Let's take a little bit to think about that. So we asked the question, delete max operation in max binary heap at the left. This is supposed to be a max binary heap. It resulted in this one. This is also a max binary heap. Whatever this element was moved from here to here. So the question is, how did that happen, and what could be the possible keys that could fit into this thing here? So what we are thinking about is that because it's a max heap, this element has to be less than or equal to n. So it's got to be the left of n, this element. And because here it was max heap, we know that that element has to be greater than or equal to h and g. So it has to be greater than or equal to h and g. Right? And then, what are the possible elements? So the possible elements are h, I, j, k, l, m, n. So we know it's greater than or equal to, it's less than or equal to n. but greater than or equal to h and g. The question is, why didn't I put g here? The reason is if I put the g here, it would violate the heap order property. So because you couldn't have g and h here, right? Because g is bigger than, well, see, you have g, h, yeah, g is smaller than h, so g, e, f, g, h, yep, g is smaller than h, so it should be here. So the g couldn't be the possible thing. So that's one of the things that we will think about. Okay, so building a heap. Let's talk about building a heap. Building a heap is if you're given an element, so uh, it can be top down. We can build it top down. That means, data comes in. I will try to insert elements with an empty heap, and as they come in, I'm going to insert them, and each one takes log n operations. Uh, Assume that the n data elements are inserted to the heap, then each one takes n log n, and therefore, each one takes log n, and all of them takes n log n. So that's the cost. The question is, can we build a heap better than n log n? Suppose the use case is static data set, so we know the data in advance. So we start with a random element. We put all the elements randomly into whatever the order, from 1 to n. And then starting from the bottom of the tree, assert that each node satisfies the heap order property, otherwise fix it. So the goal is, let me just explain to you how it's done. So here's a heap, and what we do is we maintain a max heap at each node all the way to the top. So so the demo would be something like that. And then mathematical analysis of the bottom-up build heap would be that given a binary heap of height h, there are at most 2 to the h plus 1 elements there, minus 1 elements there. And so the bottom row has at most 2h elements that already satisfy the heap order property. By themselves, they are heaps below them. And the previous level has 2 to the h minus 1 elements that may have to sync at most one level for a total of 2 to the h minus 1 operations. The one up previous level has at most 2 to the h minus 2 elements that may have to sync at most 2 levels each. And the root will sync at most h levels and to have an operation of just one element. So if you add them up, what you get is that you get the sum h 2 times h minus 1. There are 2 elements here that will have to come down h minus 1. The next level is 4 elements come down h minus 2, and so on. And so we have this summation. And you can assume for analysis purposes, it's a complete tree. It has all the entries in there. And because we are doing syncing, we have to do 2n compares, because we have to compare with both children before we decide to come down. And then we do one exchange. And I think the trick here is that can you prove that this is actually a linear time construction? So the best way to do that is to really write this as bound this by an integral from, let's say, I think we can say 2 to the, 2 to the h minus I. So it'll be 2 to the2 to the I h minus I. And that integral, if you do it, you can prove that that's the case. I encourage you to go do that, right? Okay, now let's take a look at the actual code that we can write. So I guess we talked about 2 functions, insert and delete max. Those are the main things. So in the insert, we want to insert a key into the priority queue. And what we do is we increment the n is the last index. We increment the array n index by 1, and then put that into the end of the array. That means it's the next leaf that we are building, and then swim that n all the way up to the top if we have to. All right. So how do we swim something to the top? So what we're saying is that while the k, we want to swim k. So in this case, k is going to be n. But we can swim something from any index k up up the root. So as long as the parent of k, which is k over 2, is less than, we want to do an exchange and go up one level. So essentially, I think you can convince yourself this code, actually the worst case behavior of this code is that if you start from k equals n, a code runs log n time, and it's fairly simple code. The only thing you want to make sure is that as you swim this key up the priority, the tree, it still remains a heap. That's one of the things. So this, we have to ask that question: does this code really works? So we may have to violate the invariant of the heap property, because we assume that before we insert it's a heap, and after we insert it's still a heap, right? So that's important. And we know that this is going to be at most 1 plus log n compares, because it's the height would be the log n, and then if you're going to swim all the way up to the, so it's one more than the number of edges. Delete max works like this. So we say, okay, max is the first one. Then we exchange the one with the n and decrement the size of the queue because we are deleting it. And now we are syncing one. And then just to be safe, we will make that last thing null and return the max. So to think, what we have to do is that we will write a piece of code. Again, you have to convince yourself this code runs in log time. Again, pre and post conditions are: before we delete max, it's a priority queue. After you delete max, it's a priority queue. I mean, it's a max heap, right? So here, what we're saying is, okay, so if you're given some j, which is, let's say you're trying to sync k. So k is the element. So 2k is the left child. So we compare the left child to right child. So j plus 1. So if the left child is less than the right child, so we have to compare with the right child, right? The right, because left child is less, so we have to worry about the right child. So we increment by 1. And then we compare the k with the right child. If k is greater than the right child, so we are good. Otherwise, we're going to exchange it and then go to the next one. So you can convince yourself this code really works. So here's the max PQ code so far. We create a priority queue, say a fixed size, but you can change this because you can do this in amortized time, a good amortized time, by using an array, doubling the array when you need more space, as long as we have the space. Now we have the insert delete max, which has helper functions, swim and sync, empty, check whether n is 0. And then we have two functions that will allow us to make use of the keys compared to function, and exchanges that allow us to exchange two indices of the array. So these are the two helper functions we will use to inside our code. All right, so let's have a little discussion about the binary heap invariance. How do we think about binary heap invariance? So first invariant is that we want before insert and after insert the heap to be a heap, or before delete max, after delete max heap to be a heap. So we want to check whether something is a heap. This is the main condition we are checking. We want to make sure for all the elements except I equals 1, the parent is greater than or equal to the child, which is important. If it's not, then we return false. Otherwise, return true. So we look at, this is the condition we like to have in the heap. This has to be true. If it's false, then we're going to return false. One of them is false, right? So that's the heap. You can also write a recursive method to check that. You can check whether left child is a heap and right child is a heap, and the parent is a heap. But in the insert function, so we had something called swim. So insert to the end and we swim up. So we want to find a strong invariant for swim. The idea would be that when you insert at the end, it might be violated. The ordering invariant might be violated. So it's not a heap for a little bit, right? Um, so you have to move it up. So suppose you move it up by saying, okay, when you move it up, that it can be violated at the new index. So as the new element move up the tree when you're swimming, the heap order property might be violated at the current index. So what we need is a new function that checks if a given object heap is almost a heap, except the parent of the current node, n might be smaller than n. So we're going to define a function called isHeap except up. So except for the current element up, it is a heap for any element n. So it's literally the same as isHeap. So for example, if n happens to be 1 except up 1, it's a heap. But because there's nothing up 1, so it's a heap, right? So it's really the heap except that. So except if the index I equals in, we don't compare with the parents. Okay. So here's the heap except up method. Essentially, this is fine, but what we're again saying is that unless it's k or 1, we don't check it. We want to make sure that the parent is always greater than or equal to I. Otherwise, it's false. All right, so that's really, we are doing it for all the n here except for kn1. All right, so when you write the swim method, essentially, we can write, this is our swim method, k, while k is greater than 1 and uh, k over 2 is less than k. And the loop invariant is, we say this is a heap when you enter this except up, right? So I don't think we have to go through the proof of this. Essentially, we have proof that it's true at the beginning of the while loop. It's a heap except for k, right? So when you come to the k, obviously, if you go back and look at it here, if it's k, obviously it's true, right? Except for k, it's true. And then if you go into the loop, then we know that PQ of k over 2 is less than PQK. So we're going to do the exchange. And now it's true, again, true at the end of the while loop. So that means it remains true throughout the loops. So in the case we go all the way to k equals 1, we know that the loop invariant was true and k equals 1. So this means is heap except up 1, which is the same as is heap, right? Otherwise, if you leave early, that means we know the up methods are down. We can create a more formal proof, but that's really some argument there. I think the main method lesson here is that we want to think about invariance for data structures where it's violated, temporarily violated, but eventually it's fixed. You can think about writing a loop invariant for the other one too. All right, so the next question you want to ask is, can we improve this idea of a binary heap to say, a D-Way tree? So here's a tree with 3 children. We could do that. It's the same idea. Parent keys no smaller than the children keys, greater than or equal to the children keys. I think that's, I believe this is true here. Oh, I guess not. This is not a heap, so we have to fix this. So we could fix it by starting from the bottom. So that's a heap. This part is fine, right? It's Mac heap, k element, but you have to fix the other things. So for example, we have to make sure that we sync these things so that they become a heap. Okay, so do something here. Anyway, I think the idea would be that if we do this, we can think about the same idea, sort of inserting to the next one and deleting it. It becomes a little complicated, but you can say the children are 3k, 3k plus 1, 3k plus 2, and you can pretty much write the same code. Your height becomes a log base 3, but you're also doing, instead of 2 comparisons, you have to do 3 comparisons now. Going up is still one comparison. I think coming down is three comparisons. Okay. So next we're going to take a look at a demo of a priority queue. So the idea here is that we want to talk about some event-driven simulation, which is an application of priority queue. So let's suppose that we have a bunch of particles, random particles that are in a unit square. They bounce off the walls. They're moving at a certain speed, certain time. So essentially, we want to kind of have bouncing balls. So if you write a simple program, you can write a program like, so suppose we have a ball element which has a size and a position and a velocity, both in x and y directions. And we create a bunch of new balls here. And then we standard draw, we clear everything, and then move the things a little bit. We draw the ball, and then we do the standard draw. We kind of delay the main simulation loop, right? So that we delay a little bit and then show that. I'll show you a demo of that. So this is going to show some kind of balls kind of moving in their own way from a random position. But if you want to come up with some more compelling demo, we want to have something like a colliding ball. So for example, if you have two balls and they are colliding, we want to think about at time t, the ball is here, at time t plus some dt, where we choose what dt is going to be in our program. And so it gets closer, and t plus dt, it has gone a little bit farther than we want. And then we know that t plus delta t, roll back a little bit, and then it collides. And then whatever the rules of collision, we'll try to send them in opposite directions, or we change the velocity and so on. So a simulation is too slow if dt is very small, and if dt is large, we may miss things. That's the thing. But the problem is, the drawback here is that if you want to have n particles to check whether they overlap per time quantum, which is dt, it takes n squared over 2. That's a lot of work to do. So what we're going to do is we're going to come up with the idea called event-driven simulation. Change the state only when something interesting happens. So between collisions, we will assume that particles move in straight line, and focus only on times when the collisions occur. So what we will do is maintain a priority queue of collision events prioritized by time. So it will have the next event at the front of the queue. So we get the next collision when you delete the minimum. And so the simulation loop works like this. We fill the priority queue with all potential particle world collisions. And so there can be up to n squared things in there. And then fill the priority queue with all potential particle-to-particle collisions. So you can have a particle can collide with the walls or collide with the particles. And then, in the main loop, let's delete the next event from the priority queue, minimum priority t. If the event has been invalidated, that means some other thing has happened and it's gone out, we can ignore it and advance. We can check that by looking at certain things. Advance all particles to time t to a straight line trajectory, and update the velocities of the colliding particles, and then predict the future particle wall and particle-particle collision involving colliding particles and the insert sequence. Because we know that other things are moving, but we know which ones are going to collide the soonest, and we take care of that. Then we take care of the next things and the next things and so on. So that's the whole idea. So let's do a demo. So here's a demo with an elementary priority queue. Okay, so let's take a look at some of the examples of that. Most of this code is from the Sedgwick, Wayne, who are faculty at Princeton, who are my colleagues. I often teach the course with them. And most of the code has been developed as part of the textbook. So it has a particle Java, minimum priority queue Java, and so on. So the first thing I'm going to show you is that if we use an elementary implementation, that means we use an unordered array. That's the minimum priority queue bad priority queue, so which is kind of implemented here. What it does is essentially, if you look at the how it does the insert. It doesn't really do anything. It just insert to the end. It doesn't adjust anything. But if you have to delete min or find min, you have to do some work. So you have to do n work here to find the minimum. And to delete the minimum, you have to do n work. So this loop runs n times. So what we're going to look at is that this collision, we're going to run this system. Let's see here. So we're reading a bunch of things from a local file called diffusion.txt, which contains some particle information. You can run this for 1000 milliseconds. So let's see what happens with this bad thing. So again, I want to make sure that, okay, so minpaq bad here. There's another place that I use the minpq bad. Okay, here it is. So I want to use the minpq bad here. That's for the simulation part. And now I'm going to run this. So let's see what happens. Now this is how the particle systems will behave. Notice that the things are getting slower. It's going to run for 1000 milliseconds. And if we wait a little bit, I think we're going to see things coming back here, things coming back, and essentially that was it. Right. Now, let's assume that we use a good binary heap implementation of priority queue, which is log n time. So I'm going to go and change this here. Let's see here, and then run the same program. Essentially, I change the implementation of the priority queue and see what happens. Notice how smooth it is right now. And just by changing from an array to a binary heap, made this a very compelling simulation. So that's really pretty much the end of this lecture, and thank you.